Welcome to the online video lecture series of the course Computer Organization and Architecture. In this module of the course, we have talked about various types of memory. We have talked about memory hierarchy and their uses and their organization. We have also talked about how the mapping between one type of memory to other type of memory is done. That we have also discussed. We have also talked about virtual memory concept, which helps programmers to store large programs or multiple programs in a auxiliary memory space. And we have also talked about how main memory is mapped with the logical memory or virtual memory. Now, in today's lecture, we will discuss various types of numerical problems related to memory organizations that are important as far as your university exam is concerned and other competitive exam is concerned. Let us see the first numerical problem. A computer's main memory consists of 1024 blocks. It is given as 1024 blocks and 256 words in each. That means main memory size is given as 1024 blocks, where one block size is 256 words. So, this can be converted into number of words. So, what is main memory size in this case? Main memory size is 1024 multiplied by 2 to the power 8 or 256 words. So, that comes as 2 to the power 18. So, 18 bits can be used to address the main memory, or address is used in case of main memory of 18 bits. Now, second part of this numerical, the cache memory has 8 sets of each having 4 blocks. So, that can also be converted into number of words, because one set is equal to 4 block and there are 8 sets. So, cache memory size is 8 sets, that means 2 to the power 3, and one set equals to 4 blocks. So, it will come as 8 multiplied by 4 multiplied by 256, because in one block we can store 256 words. So, cache memory size will come as 2 to the power 13 words. So, 13 bits are required to map the cache memory. Now, the next part is we have to determine the length of tag, set and word fields in the main memory. So, as we know, the main memory address bits are divided into two parts, that is tag part and index part, where index is nothing but it is equal to the size of cache memory. So, index will become as 13, because cache size comes as 13 bits. So, remaining bits, that means 18 minus 13 will be equal to 5. So, tag size will be equal to 5 in this case. Now, in case of set associative mapping or direct mapping, the index is further divided into blocks and words. So, how many blocks are there in cache memory? There are 32 blocks you can see here, because in there are 8 sets and in each set there are 4 blocks. So, 32 blocks are there in the cache memory. So, that is why 5 it comes as 5. Now, number of bits for map the block is equal to 5, and for word in each block there are 2 to the power 8 words or 256 words. So, that is why it comes as 8. Now, in case of direct mapping, the tag bit value equals to 5 and block word equals to 5 and word bit equals to 8. So, total becomes as 18, because total size of the total number of bits for main memory is 18. Now, in case of set associative mapping, we have to calculate how many number of sets. As given in the problem, there are 8 sets. So, how many bits are required for map these sets? 3 bits. That is why in place of set it is given as 3. And for one block, how many words are there? There are 2 to the power 8 words, 256 words. So, that is why it comes as 8. So, in each block 2 to the power 8 words and there are 8 sets. So, that is why 3 bits are required. And now we have to calculate number of bits for tag. So, main memory in case of set associative mapping, this is divided into tag, set and word. So, total is 18. Now, 8 plus 3 equals to 11 and 18 minus 11 equals to 7. So, that is why tag value will be equal to 7. So, in case of set associative mapping, so this value will come as 7, 3 and 8, and in case of direct mapping, this value, the tag, block and word will be equal to 5, 5, 8. Now, come to the next problem. In this problem, the main memory size given as 64 MB. So, MB means megabyte. So, in each word there are 8 bits. In each word there are 8 bits. That is why it is given as byte. 64 M means 2 to the power 6, 2 to the power 20. So, it will become as 2 to the power 26. So, 26 bits are required for main memory address. And next part of this, 32 KB is the size of cache memory. So, cache memory size 32K means 2 to the power 5 multiplied by 2 to the power 8, and byte means there are 8 bits in each word. So, we have to consider the left portion of this cross. This cross means we have to consider only address part of this memory or this word. So, this will become as 2 to the power 15, that means 15 bits are required to map the cache or to address the cache. Now, the mapping between main memory and cache memory means 26 bits will be mapped with cache memory, that is 15. So, mapping between 26 to 15 is required. Now, in this question what is given, each line in the cache stores 8 bytes. Each line here in this case, line means block. So, one block equals to 8 bytes, that means 2 to the power 3 number of words can store in one block. Now, the question says show the format of main memory address or memory address for the direct mapping. In this case, the direct mapping is asked. So, in case of direct mapping, we have to calculate the tag bit, we have to calculate the index bits, then we have to calculate number of blocks and number of words, bits for number of blocks and bits for number of words. Now, calculate the index size. Here 26 bits are required for main memory address and 15 bits are required for cache memory. So, index size is nothing but it is equal to the address bits for cache memory, that is 15. So, index size will comes as 15. So, remaining bits means main memory address minus index value will become as tag size. So, tag size will be equal to 11 in this case. Now, next part of this question says how many number of lines are there in the cache. So, we have to calculate number of lines or number of blocks. So, how this can be calculated? So, it is very simple, number of blocks or number of lines can be calculated. What is the total size of the cache memory divided by one block size or one line size. So, here in this case cache memory size is given as 2 to the power 15 and block size is given as 8 bytes. So, 2 to the power 3, that is, so it will become as 2 to the power 12. So, in this case number of blocks are 2 to the power 12. So, 12 bits are required for block mapping. Now, we can easily map in case of direct mapping tag, bits, block and word. So, how many bits are required for tag? It is 11. We can write here simply. How many bits are given for index? It is 15 as we have calculated, and this index will be divided into two parts, that is block and word. So, number of blocks comes as 12 to the power 12. So, 12 bits are required for block mapping, and in each block there are 2 to the power 3 words. So, 3 bits are required. So, that is why it is calculated as 12 and 3, 12 bits for block and 3 bits for word in each block. So, this way we can solve this such type of problems of direct mapping and set associative mapping. Now, come to the next problem. In this case, a block set associative mapping we have to consider, and cache memory consists of a total of 64 blocks. So, here 64 blocks are given. So, we can write here cache memory size equals to 64 blocks, or you can say 2 to the power 6 blocks. Now, next is divided into 4 block sets. 4 block sets means in each set there are 4 blocks. So, this is 2 to the power 2 number of blocks in each set. Now, in next part of this, the main memory contains 4096 blocks, each consists of 128 words. So, 4096 blocks means 2 to the power 12. So, this comes as 2 to the power 12. So, this can be written as here 2 to the power 12 number of blocks, and in each block there are 128 words. So, we can calculate the main memory size in terms of words. Simply you multiply with 2 to the power 7. So, cache memory and main memory can be converted into number of words. So, how many number of words are there in cache memory? 64 into number of words or the block size, that is 128, because in each block we can store 128 words. So, this will come as 2 to the power 13. The cache memory will take 13 bits, or the index size in this case is 13. The index size is 13 bit. And the main memory, similarly we can calculate 2 to the power 12, because there are 2 to the power 12 number of blocks as we have seen, and into 2 to the power 7, because 128 number of words in each block is given. So, this can also be calculated or observed as in terms of words, that is 2 to the power 19. So, main memory will take 19 bit address total, 19 bits address for main memory is required. Now, we have to map. We have to map this 19 bit data or 19 bit address with the 13 bit cache memory address. Now, in first part, what is asked, how many bits are there in the main memory address? So, we can easily calculate 19 bits are required in case of main memory, and how many bits are there in tag set and word field. Now, in this particular problem, it is given as in one word in one block there are 128 words. So, 128 means 2 to the power 7. So, 7 bits are required for words. And how many number of sets are there? So, we have to calculate number of sets. In this case, it is given already, it is 4 blocks, and which will come as one block is to one set equals to okay. How many number of sets? We have to calculate number of sets. Total number of sets in this case, what is the size of cache memory? How many number of blocks? There are 64 blocks, and in each set there are 4 blocks. So, it is divided by 4, it will come as 2 to the power 4. So, 4 bits are required to map the sets. And what is the total size? Total size of main memory is 19. So, 7 plus 4 equals to 11, 19 minus 11, that will come as 8. So, 8 bits for tag is required. This way, we can solve the problems related to set associative mapping. So, terminology will be changed in different type of numericals. You have to concentrate what is exactly given in the problem. We try to calculate in this way. Now, in next problem, a computer system has a main memory consists of 1 mega 16 bit word, means 1 megabyte or 1 mega 16 bit. In each word there are 16 words, you can consider. It also has 4K word cache organized in block set associative. This is a problem of set associative memory again, and 4 blocks per set is given, and 64 words per block is given. So, everything is given in the problem. We have to map only. We have to systematically solve this problem. Now, cache memory size is given as 4K as given here. This is 4K. So, it will come as 2 to the power 12 cross 16. So, do not bother about this data part. We have to consider only address part, which is given left side of this cross. So, 4K means 2 to the power 12 words. So, 12 bits for cache memory, and in each set there are 4 blocks, and in each block there are 64 words. So, we can calculate the cache memory size in terms of word also. Now, next part of this, main memory will be having size of 1 mega 16-bit word. So, don't bother about this right side of this cross or data part, only you have to concentrate on address part, that is 1 mega. So, in this case it comes as 2 to the power 20. So, 20 is the size, 20 bits are required for main memory. No, yes, it is given in terms of words, no issues, 20 bits are required for main memory. So, address size in case of main memory is 20 bits. Now, total number of sets in cache memory, what is that size in terms of block? So, cache memory has 2 to the power 12 as we have already calculated, divide by how many number of blocks? There are 2 to the power 6, because in each set there are 4 blocks and in each block there are 64 words. So, this has to be divided with 2 to the power 12. So, it will come as total number of sets, in this case 2 to the power 4. 2 to the power 4 means there are 16 sets in the cache memory. So, 4 bits are required for set as we have written here. So, for set 4 bits are required, and in each block there are 2 to the power 6 words. So, that is why it is given here 64. So, 6 bits are assigned for word, because in each block we can store 6 to the power 6 words. So, 6 bits will be given to word part and 4 bits will be given to set part, and remaining means there are 20 bits for main memory address. So, 20 minus this 4 plus 6, that is 10. So, 20 minus 10 will become as 10. So, 10 bits will be given to tag. So, this way we can solve the next problem. Now, in next part of this lecture is one more problem is given related to mapping or direct mapping. A digital computer has a memory unit of 64K cross 16. So, again main memory size is given as 64K, that means 2 to the power 16. So, do not bother about right portion, again it is a data part. So, you have to focus on only address part. So, it will come as 2 to the power 16 words. Now, cache memory size is given as 1K words. 1K means 2 to the power 10 words. So, obviously, in this case also the word size will be equal to 16. So, 1 word equals to 16 bit. So, do not bother about data part of the word, we have to consider only address part. And what is given next? In each block we can store 4 words. So, 1 block size equals to 4 words, 2 to the power 2 to the power 2 words in each block is required. So, how many number of blocks are there in the cache memory, that we have to calculate. So, what is the cache size in this case? 2 to the power 10 as we have already calculated, divide by block size, that is 2 to the power 2. So, it will come as 2 to the power 8. So, 8 bits are required for block, 8 bits are required. Now, as we have already done, main memory size is divided into 2 parts, tag and index. Index size equals to cache size. So, that will equal to 10, and that index is further divided into block and word bits. So, 8 bits for block we have already calculated, and in each block there are 2 to the power 2, that means 2 bits are required for word. So, 8 and 2 are given to block and word. Remaining bits, remaining is 6, because the main memory address bit size is 16. So, 16 minus 10 equals to 6. So, tag will come as 6 in this case. Now, next problem is again a problem related to, this problem is related to virtual memory. So, an address space is given as 24 bits and the corresponding main memory space is 16 bit. So, we can write the address space is 24 bits and main memory in terms of M, that is 16 bit is given. How many words are there in address space? Obviously, if n is given as 24, so address space will become as 2 to the power n, that means 2 to the power 24. And similarly, the main memory or memory space will become as 2 to the power m. So, this will be equal to 2 to the power 16, 2 to the power 16. is the size of main memory. Now, in next case, if a page consists of 2k words, how many pages and how many blocks are there in the system? Obviously, the page size will be equal to the size of block, because in case of virtual memory concept, the pages are shifted into a block. Obviously, their size must be equal. So, page size equal to block size. So, in this case, the pages are because in the virtual memory is converted into number of pages and main memory is converted into number of blocks. So, we have to calculate page number of pages, and page size is given as 2k. Obviously, this will equal to the block size. So, 2 to the power 11, 2 to the power 11 2k will be equal to 2 to the power 11. So, 11 bits are required for paging and block, and for block also. So, number of pages we can calculate using address space, and number of blocks we can calculate using memory space. So, what is the size of address space? That is calculated as 2 to the power 24, and one page size equals to 2 to the power 11. So, it will become as 2 to the power 13. So, obviously, how many number of pages? 8k pages. That will come as 2 to the power 3 multiplied by 2 to the power 10. So, this is 8k number of pages are there in virtual memory or address space. And similarly, you can calculate number of blocks using this formula. Memory space divided by block size. Memory space is equal to 2 to the power, this is wrongly written, this is 2 to the power 16, this is 2 to the power 16, yes. So, memory space we have already calculated 2 to the power 16, and one block size equals to 2 to the power 11, because 2k word is the size of block. So, it is divided as given here 2 to the power 16 divided by 2 to the power 11, it will come as 2 to the power 5. That means 32 blocks are there in the memory space. So, this way we can solve the problem related to virtual memory. One more problem related to this, the logical address space in a computer system consists of 128 segment. It is a problem memory management hardware, or where the virtual memory is converted into number of segments, and there are 128 segments of varying size, and each segment can have up to 32 page of 4k words in each. So, physical memory consists of 4k blocks of 4k words in each. Obviously, once the page size equals to the size of block. So, first logical space we will calculate. Logical space is given as 128 segments, and in each segment we can store 32 pages. So, we can calculate the total number of bits for logical space. So, one segment equals to 32 page, that means 2 to the power 5, and one page equals to 4k words. So, that will come as 2 to the power 12. So, this way we can solve the problem. The data is given. Now, the logical address space, as we have already discussed in virtual memory concept, or the lecture or our previous lecture, where we have done this mapping or logical mapping, logical address mapping, where logical address is converted into 3 parts: segment, page and words. So, how many segments are there? We can see here 128 segments. So, how many number of bits are required? Because 128 equals to 2 to the power 7. So, 7 bits are required or assigned to the segments, and each segment there are 32 pages. So, that is why 5 bit is given here for paging, and in each page there are 2 to the power 12 words, which is given as here 4k is the size of one page. So, it will come as 12. So, we can easily give this value in this segment, page and word. We can map the segment, page and word, which is already calculated. 7, 5 and 12 are assigned. So, logical address will become as total of this, that is equals to 24. And the physical memory, because physical memory or memory space is converted into number of blocks, and in each block there are 4k words. So, there are 2 to the power 12 blocks as given here already in this problem. Here physical memory is given as 4k blocks. There are 4k blocks, that means 2 to the power 12 number of blocks are there, and in each block there are 4k words. So, 12 is given to the number of blocks and 12 is given to the number of words. So, this way we can assign physical memory, that is 12 bit for block and 12 bit for word. Now, come to the next problem. Here in this case, a virtual memory has a page size of 1K words. One page size equals to block size, that is equals to 1K word. That means 0 to 1023 will be the value of address, because this is equals to 2 power 10. So, that is nothing but 1024. So, address may vary from 0 to 1023. Now, there are 8 pages and 4 blocks. There are 8 pages and 4 blocks. So, virtual memory equals to 8 page and physical memory will be equal to 4 blocks, because virtual memory is divided into number of pages and main memory is divided into number of blocks. That is why 8 pages are assigned to virtual memory and 4 blocks into memory space. So, at a time only 4 pages can reside in block, that we can understand. Now, what is given next? The associative memory page table contains the following entries. This entry is given because this page number is available with block number 3, 1 number page is available with block number 1, 4 number page is available with 2 number block and 6 number page is available with 0 number block. So, you can see only 4 pages can reside in main memory in different blocks. So, remaining pages will come under page fault, or remaining pages are not available in main memory. So, make a list of virtual addresses in decimal that will cause a page fault. Obviously, remaining pages will come under page fault. So, how many number of pages will come under page fault? 4. And what is the sequence of those pages? That is 2, 3 and 5 and 7. Now, we can map or we can assign addresses to each page. So, page number 2 will be of size 2K as given already. What is the size of page? That is 2K. So, this will come as 20482 the size of one page equals to 1K words. So, it will take 1024 decimal places, okay, decimal values. So, the 2 number page will start with 20, because 0 to 1023 will be the first page or first page address, and 1024 to 2047 will be the second address or address for second page, and likewise we can assign different values for page fault. So, 3 will be having 30724096 decimal values, and 5 will be having 51202 6143, and 7 will be having 716828191. So, this way we can solve the problem related to virtual memory or mapping between virtual memory to main memory. So, that is all about this particular lecture. We have done various numerical problems related to this unit. Thank you.